So today I'm going to be lecturing on DP optimizations, specifically divide and conquer and Knuth optimization. So the reason I'm doing both in one lecture is because they both use this idea of monotonic transitions. So I'm just going to go ahead and start with divide and conquer DP. So divide and conquer DP solves the recurrence of dpij is equal to min over 0 equal to j of dp I minus 1 k minus 1 plus some cost k to j. So when would you see this type of recurrence? So if this first state, if we have m states for here and we have n states here, so the total runtime would be like O of m times n squared, right? And so you would see this in problems where you have some array, right? And that would be like your n, and then your m would be like the number of contiguous subarrays you want to partition it into. So if you partition it like this, like into m subarrays, and then you get some cost of these subarrays, so like cost 1 plus cost 2 plus cost 3 plus cost 4 plus cost 1. And you want to try and minimize pretty much this this cost. So this idea of like monotonic transitions, it's pretty much like if you have let's say opt ji, or opt ij. So this is like our I subarray we're on. And this is like our the index we're on. We're on our jth element. And so what opt ij stores the optimal transition from some j that minimizes this recurrence pretty much. And so if we can prove that this optimal transition is less than optimal transition of I to j plus 1, then we can use divide and conquer dp. And so one condition, or one sufficient but not necessary condition for having this like monotonic transition is having something called the Quadrangle inequality, or the Monge condition. So when our cost function follows this like quadrangle inequality, where we have like some a less than or equal to b less than or equal to c less than or equal to d, if our cost from a to c plus cost b to d is less than or equal to cost a to d plus cost of b to c. If this is true, then we satisfy our quadrangle inequality. And it's called the Monge condition because this condition satisfies something called a Monge array, or a Monge matrix. So I'm going to draw one out really quick. So if we have the matrix like 10, 17, 13, 28, so it turns out like, so Monge matrix is special because if you pick any submatrix here and you pick the corners, like if we take this submatrix here with 10, 24, 22, and 13, the sum of this diagonal will always be less than or equal to the sum of this diagonal. It's like 10 plus 22 is less than 13 plus 24, and like 10 plus 22 is less than 17 plus 17. right? So that's true for any submatrix you choose. And that pretty much defines a Monge matrix. So what are the properties of Monge matrices that allow us to have this sufficient but not necessary condition for like a monotonic transitions, right? So one property of this is that this bidirectionally like implies like cost of I, cost of I, j plus cost I plus 1, j plus 1 is equal to cost of I, j plus 1 plus cost I plus 1j. So it turns out like these two things like imply each other. So that's like one thing useful to know. Like if you can prove this or this, either one works. And the most important like property of Mongeries is like you can. So in our cost matrix, we only need to consider ranges where the L is left less than or equal to the R, right? So this kind of doesn't make sense for if we consider our R to be like our column. It doesn't make sense to have like these like extra values. Like they kind of don't make sense. So for our purposes, we can like modify our matrix such. And so like you kind of get like this triangle shape. And it turns out when you go through each column and you find the topmost row such that it has the minimum value and we circle them. So 10, 17, 13, 17. It turns out like every time you go right, you also go down, right? And so like this kind of guarantees our monotonic condition. And so, but it's not intuitive like why this is true, right? And so there's a nice proof by contradiction you can do, where you say like if like for adjacent columns, if you have some like minimum here and minimum here that violates our like property, we can see that if we choose this to be like our submatrix, and like we have these 4 values here, this sum will be greater than this sum will be greater than this sum over here, this diagonal, which is the opposite of what we want. So like that pretty much contradicts why you can't have this case right here, right? And so that's that's why like having this quadrangle inequality guarantees that you have your optimal transitions are always monotonic, pretty much. So for the actual like algorithm for doing the divide and conquer, we have like you could naively do it, but that takes O of m times n squared time. That's obviously too slow. But if we know we have this like monotonic transition thing, we can do like kind of like a binary divide and conquer. So what we initially set our for our very first state, we have like every transition is just equal to the first value. So if we have our array, let's just set the optimal transition to be this guy right here. Right? And then what we can do is we can relax it k minus 1 times or m minus 1 times with our divide and conquer, and we'll be able to get our answer. So how does the divide and conquer actually work? So if we have some compute function, like, oh sorry, any questions so far? Sounds good. Yeah.
So when you say like you're setting up like the first transitions and then we're gonna relax them.
Yeah.
But like, what are the first transitions? Are we like?
Yeah.
Or what do you mean by that? Do we pick like one transition for each state?
So for like every index, you set its optimal transition to be the first guy, or the first element in the array. So it'd be like,
Oh,
yeah, you initially set it to be like cost of 0 to j.
I see, because we're doing our DP where it's like looking backwards.
Yeah.
Like the first guy, I think.
So that's where our initial guys will be.
So it's like that whole prefix.
Yeah, it'll be the entire prefix.
Mm-hmm.
So now we have to do the relaxation. So it makes more sense if we think of this like not as a 2D DP, but we do like a state reduction, because it only depends on our previous row, right? So we can just use that like to relax, or just our previous row. So we have some function compute. That stores the left range, right. This stores like the subarray we're looking at, and we have like int opt L, int opt right. Right. So what we do is first we compute the mid, which is like mid is equal to L plus R divided by 2. And then we're going to transition on all, so this is the current index we're looking at, and this is the current index we want to find the optimal transition to. So we can loop from our for, like opt L to opt R. In the very first iteration, like this will be like 1 to n and 1 to n, right? So we find let opt equal the best transition for this mid guy. So we loop from opt L to opt R, and then we can recurse from like L to mid minus 1, and then opt L to opt, and then compute from mid plus 1 to R, opt, and opt R. So the idea behind this is like we find our mid for this current subarray, and for the left half, if we know our optimal transition, because it's monotonic, we know that anything to the left of it cannot have a optimal transition bigger than opt right here, and it's the reverse for the right half, right? And so, yeah, so if we just run this like k minus 1 times, using like the previous row from our DP and then computing our new row for our DP, then we can compute this in, we can compute this entire DP in O of n nm log n, as opposed to n squared log n. So does this make sense? I'll go over why it's nm log n, but does this make sense, like what we're doing here?
I'm trying to understand when you say so we have this mid, and then you're saying we're trying to find best way to transition to that mid.
Mm-hmm.
Well, what exactly are we like solving? What's the problem we're addressing?
We're trying to solve this recurrence, pretty much. We're trying to find the best transition that minimizes this recurrence. Okay. And like, yeah. So I minus 1 is just the previous row for DP, pretty much.
Okay.
So yeah, we're just trying to minimize this this recurrence. So I think it'll be more clear, like if we do it like in a diagram or something. So it's not immediately obvious why this reduces it to nm log n. So assume we have our array, right? Let's just say in the perfect world, like our splitting point is in the middle every time, right? So we get our mid, and then we subdivide into 2 ranges, right? And then we subdivide it into again. Notice that in every, like these bounds store, like, so this is for our first mid 1, mid 2, mid 3, so on. So eventually we get like, we're trying to find the answer for 1 mid here, 2 mid here, 4 here, and 6, and 8 here, and dot dot dot. So like the summation of all these will equal like to sub power of 2, and that's why we only have log n levels. And so if our optimal transition, let's say in a perfect world, was split in half every time, we see that for this guy, he only has to transition on this half, and this guy, he only has to transition on this half, right? So it takes O of n transitions here, and it still takes O of n transitions here, and O of n transitions here in total. And if we add them all up, we get O of n log n. Right? But the optimal splitting point is not always in the middle, right? Sometimes it'll be like, it can be skewed to one side or the other, but it doesn't matter, because if we have our array, right, and we split it like not evenly, it doesn't matter because let me draw one more layer. So like these are not even, but they still take O of n time in total, right? This still takes O of n time. This mid guy, he only gets access to this range to loop over, and this mid only gets this access to this range to loop over. So that's why like in our conditions we set like the bounds for these to be, right? So this still only takes O of n time per layer. And that's still O of n log n.
Wait, Sathvik.
Yeah.
If your splits are like uneven like that,
Yeah.
you have more than log depth.
No, you can't have more than log depth because of what we explained here, right?
Mm-hmm.
There's in every step we're computing the answer for some index, and we're choosing that index to be the mid of the range every time. So at the first layer we're only computing 1 mid. For the second layer we're computing 2 mids,
Mm-hmm.
and the third layer we're computing 4 mids. Those are all each different indices of our array. So we can only have log n depth because that's like, this becomes like 2 to the x whatever is less than or equal to n. I take log of both sides.
Mm-hmm.
What? So how could we have skewness like this drastic if it's the mid? Is it always just like off by 1, or could it be?
No, it could be like if you're trying to like if you're let me erase some of this stuff. If you're at let's say this is your array, right? Add some more ones. So like let's say this is your mid, right? You still divide the range evenly in half, but the optimal transitions don't get divided evenly in half. But it doesn't matter because they still add up to O of n anyway, right? So like let's say this was our optimal transition for this guy, for our mid. So then we transition onto this left half, right? I'll say this so optimal transition, and this guy, so this left half's optimal transition go from the beginning opt L up to here, right? And this guy's optimal transitions go from like all the way from here, his opt L all the way to opt R. But this is all O of n, right? This width summed up is just O of n, right? So the idea is like we are still splitting the ranges in half, but the transitions are not necessarily split in half, but their total sum will still be O of n. So like, yeah. So like this guy is still responsible for half of the array, like over here. This will be our new mid for this layer, and this will be our new mid for over here. But his transition space is this, and his transition space is this. So like if it's skewed to one side like really heavily, that'll just make that guy's range really small, and this guy's range really big, but still adds up together for O of n total. And so that's why it's O of n log n. It's O of n per layer and it's log n layers. So does that make sense? Let's see. And then like how we would like do this is, it's fine if I go over here, like we would do like for int I is equal to 1, I is less than m, plus plus, we run compute 0, n minus 1, 0, n minus 1. And if we have our previous DP store and our current DP store, after we do this compute, we say previous, or yeah, previous DP equal to new. Right. So it's like relaxing it m minus 1 times after we set our initial values to the prefix. So does that make sense? Like relaxing it m minus 1 times. Yeah, so it's so yeah, I would encourage you to like look at why this is O of n log n. Like no matter what the splits are, why it's always O of n per layer. Because I think that will give you like pretty good intuition of how divide and conquer works, and the optimization works. It's fine if I erase this. So I guess the best way to look at it is to go over a problem. So the problem I'm going to go over right now is a problem that Travis gave me, I think earlier this year. It turns out you can solve it with divide and conquer DP. So the problem is you're given some array A, 2, 3, 5, 6, and you want to split it into 2 subarrays such that the cost of one subarray is equal to the min of that range times its length. So the cost of like a subarray S is equal to the min of S times the length of S. Okay. So we want to partition it into two different contiguous subarrays. So how would we solve this? Yeah.
We'll have to partition it into 2 subarrays?
Yeah.
Is the cost the sum of the 2 subarrays?
And then yeah, the cost is the sum of the total cost is the sum of the cost of the 2 subarrays. Yeah.
So for 2 subarrays,
Mhm.
you can like brute force maybe like split and then just like finally run the range.
Yeah. So like if we only have 2 subarrays, we can just brute force the split point, right? And then we can just compute the prefix min and the suffix min, and then just do our stuff, right? But now, what if we want to partition it into 3 subarrays? What happened?
Brute force 2 points.
Okay, so what if n is up to like?
Minus stays the same.
What if n is up to like 30,000?
Whoa.
Yeah. How do we solve this? Yeah.
I wonder if we could use like a divide and conquer DP.
Wait a second.
So how can we know we can use divide and conquer on this?
We'd have to prove that it's like the Monge
Yeah.
transitions, right?
Yeah. So that's an interesting point because yeah, usually in 90% of these problems, you want to prove that this cost function satisfies that quadrangle inequality. but it's a sufficient but not necessary condition, right?
What do you think?
It's sufficient as in like if we have that, then we know it's monotonic for sure. But we don't need it for it to be monotonic. And it's actually kind of hard to prove that this satisfies the quadrangle inequality. So instead we'll use intuition. Right? So like if we know our optimal transition from this guy, if we know it's here, will this guy's optimal transition is it ever optimal for him to go back from this? And let's say we want to maximize this. Let's say we want to maximize this function instead of minimizing. Let's say we want to maximize it. The total cost. Does it ever make sense? Like, if this guy's optimal transition is from here, does it make sense to ever like go back?
Because you'd be getting the same min or a smaller min, and you'd have a bigger length.
Yeah. So the thing about the lengths is it's just calculating like what we really have is like every element gets counted once, except the elements get changed to the min of that range. If that makes sense. So if we transition back from here, it doesn't make sense because we're just making a smaller min, but we're not adding anything to our length because that gets all calculated anyway. We're just making a smaller min possibly for these guys, right? So like we can kind of like intuitively like prove like this will like transitions are always monotonic, and we can like just transition like we can use divide and conquer this, and so we can reduce this down from like O of 3 times n squared to O of like 3 times n log n. The reason I'm putting 3 here is because the nice thing about divide and conquer is, so the original problem was you have to divide into 3 subarrays, but you can generalize it to k subarrays instead, right? Like k less than or equal to like 10, whatever. We can generalize it to like however many we want, as long as like if it's in the bounds, right? So we can change it to like nk log n, if that makes sense. So I have one more problem here for divide and conquer. So you're at a bakery, or someone owns a bakery, and they have a bunch of types of cakes arranged in an array, right? So like type 1, 2, type 3, and they can be the same as well. Type 6, and the value of some box is a number of distinct types of cakes in that box. So. And she wants to deliver it, the owner wants to deliver all these cakes in exactly k boxes. And the cost of some box, yeah, I already explained, but the cost of some subarray, I guess, is the number of distinct values. In S, right? So if we want to partition this into 2 boxes, this and this, for example, and the cost would be the number of distinct values here plus the number of distinct values here. And so we have the number of cakes can be up to like 10,000, and the number of boxes can go up to like 50. Do you think we can use divide and conquer for this?
Yeah.
Yeah?
Yeah.
How can we prove this like a monotonic condition?
Well, let's think about that.
I'll write it up here again. So like if we have like a is less than or equal to c cost and our goal is to maximize this value, right? Yeah, we want to maximize. So that brings up a good point. So like this recurrence only works for min. So how can we change it to account for max instead?
If we negate the cost function.
Yeah, so if we negate the cost function, finding the minimum becomes, and then negating it at the very end becomes the same thing as finding the maximum. Or what we can do is here is like, if everything gets negated, right? Then we can negate it back, like multiply everything by -1.
Oh shoot.
So we get cost of A to C plus cost of B to D, and the sign flips. Cost of
So true.
D plus cost of B to C.
So we only have to prove that it's on one side or the other, and if we can prove either one of those, you can always negate, which I guess makes sense. That's nice.
Say that again?
You only have to prove that, like for the quadrangle inequality,
Yeah.
you have to prove that it's either greater than or equal to or less than or equal to always, because you can always
Yeah.
negate to flip between those. That's kind of nice.
Yeah. So, but yeah, you have to make sure the signs are always like consistent.
Right.
So if it's a minimum, we want less than or equal to, and if it's maximum, we want greater than or equal to. So how can we prove this holds for this problem here? Like if we have some indices A, B, C, and D. So like these ranges are initially A to C, this range is B to D, and these two ranges are like A to B and B to C, right? So what you'll notice is like every element gets counted the same number of times, except the ranges are not quite the same, right? So we have to prove that the cost from these two is bigger than the cost from these two. Any ideas? Yeah.
Yeah, because in the cost from A to C and the cost from B to D, you'll count more elements twice than in the cost from A to B plus the cost of B to C.
Yeah, so if we want to count like let's say we have two of the same value in here, right? This gets counted, so from up here, this gets counted twice, and from here this also gets counted twice, so those like cancel each other out, right? And most scenarios it turns out like where we place like some pairs, they'll cancel each other out. Except in this case where we have like one here and one here. This gets counted twice, but here it only gets counted once, right? So like this will always be greater than or equal to this cost down here. And so like after doing like all the casework for like where you could potentially place two of the same points, like here, like here, you'll find that this cost of having two of the same values is always greater than or equal to having like the cost here, which gives us like a green light to go ahead and try divide and conquer dp. So does that make sense?
It's weird because it's like those aren't our actual partitions because those aren't
Yeah.
like actual partitions, but
These, yes,
it's like what we need to prove
yeah,
that our partitions are gonna be good.
yeah, because of the Monge matrix, of how the properties of Monge matrix, of how I explained that every time you go right, it also goes down, which is why it's monotonic, pretty much.
I see. True.
Okay, and so that's all I had for divide and conquer DP. Any questions? Yeah.
This is like, I guess like a fairly fundamental question that hopefully clears a lot of things up for me. When you're saying, because I always do the recursive DP instead of the iterative. When you say we have this range and we're trying to figure out what guy to transition from, what does that like fundamentally mean? Like, is that saying connect a range here, or
It's saying if we're at some index in our array, what is the optimal what is the minimal index we can transition from that also holds the minimum value.
and when you say transition from, you mean like choose that index to our current index
Yeah.
as a partition.
Yeah, so like
Okay.
if we have our array and we're over here and we choose this to be our transition, we choose this to be our range, and we also have to factor in like the cost of the DP of before.
Right.
So like like this is what the recurrence solves.
Like we recurse on solving like the whole prefix.
Yeah.
Mm.
So after doing like k or n minus 1 relaxations, we find we can get like exactly m subarrays. Our answer will be stored at dp of n, whatever. Yeah, so that's all I have for divide and conquer. It's not too difficult except for the proof of why it's O of n log n, even with like not even splits. Now I'm going to talk about Knuth optimization. So, I also forgot to mention one thing about divide and conquer DP. It can be used to solve lots of problems you can use with convex hull trick and vice versa. So it's good to know. So for Knuth optimization, we have the recurrence of dpi to j equal to min This is the occurrence we're trying to solve, right? And like this form comes up a lot. Like this is usually known as range DP, where you're transitioning on, where you're trying to find a DP value for this range, and we do first over all split points that we can transition over. Like for here, if we choose split over here, then we get this range here. We add the DP values up from these two ranges, and then we sum up with the cost of the entire range. So what's the runtime of the naive for this DP?
Like n cubed.
Yeah, it's O of n cubed. Well, it turns out if we have the same quadrangle inequality, we can in fact reduce this down from O of n cubed to O of n squared. But there's one extra condition. So like if we're trying to do min again, we have to we have to flip the sign. The additional restriction is cost of B to C. So we have to cost A to D. As for the proof of correctness for this, it's kind of long, so I don't think I'll derive it. But as long as these two are satisfied, then we kind of have our monotonic condition, right? So our optimal transition matrix is kind of different this time. So what we really want to prove is that our optimal matrix follows this. Right? So the optimal transition for some range, I to j, always falls between these two. So like if we have like some range over here, let's say this guy we're checking is over here. This guy over here is like right? So it always falls between these two. And it turns out if these two conditions are satisfied, then this is also satisfied. And so why does this help? Because when we're doing our usual naive transition, we loop through all the elements in that range. But instead, all we have to do is loop through from opt ij minus 1 to I opt of I plus 1j. And if we do some runtime analysis, we get like a double summation. We can change the indices. So what can you notice about this summation over here? Like, let's say this is a number of times we loop over the elements. What can we notice? Not quite, but what I notice is that pretty much all these elements will cancel out, right? The subtraction from here will cancel out the positive term from the next iteration. So it turns out like this summation is approximately equal to equals 1 to n opt and if so what does this inner part turn into? Any guesses? Or how many transitions will we do if we're doing opt from k to n minus opt from 1 to k? Any guesses? So it turns out we're only going to be doing, like from k equals 1 to n, we're only going to be doing O of n transitions for every k. And so this turns out to be O of n squared total, which just follows from this summation that we're doing over here. So that's why if we have this, we can, instead of looping over like all possible transitions, we just loop from opt I j minus 1 to opt I plus 1j. But there's so some complications arise from this. Like, how do we ensure we compute these values before we compute this value, right? How can we ensure we compute this value? Well, something nice about this is that this range and this range are always smaller than this range, which kind of creates like this DAG-like dependency, right? So how you normally do range DP iteratively is you loop from like for I equals 1 to n, and then you loop from for j is equal to I minus 1 to 1, right? So this ensures like when we're at some index I and we're going backwards to some index j, this guy will already be calculated and this guy will also be like already calculated, because these ranges are smaller, and if we loop through this in this order, we can ensure like these guys are already calculated. So once we have our ij, instead of doing for k equals j to I, instead of what we do, we say for k is equal to opt I j minus 1 and loop up to opt I plus 1j. So this is the only change we make, and it changes it from O of n cubed to O of n squared. And so what you initially set for opt, like the base case values, dp of I, it can be whatever you want. Actually, it has no effect on the modified conditions, because what we can do is, for that range, we can subtract out all these and then add them back at the very end. So it doesn't matter what this is, so it's like some cost from I to I. And then from opt I to I will also just equal I. And that's Knuth optimization, pretty much. Any questions?
Wait, so
Yeah.
So for Knuth optimization, we have to like make sure that the conditions on the right hold with like the cost, like our quadrangle thing, and also like cost B to C and A and D.
Yeah.
And that guarantees
this.
that inequality where
Yeah.
it's like, and I think like I'm trying to visualize it. It's like as you're like scooching your pointers,
Yeah.
then like your optimal transition is never gonna like go backwards.
Right.
It's always like going forwards.
Yeah.
I see.
Yeah, it just works because, yeah, so if you do the summation I showed, it kind of shows that it'll only be O of n squared at most. Any other questions?
How would this work for max?
For max, I'm pretty sure, I think you can just flip the signs here. Yeah, I think you can just flip the signs here and you'll be fine for max. So I'll go through a problem here. So you might have seen this problem before, but essentially you're given some bar, right? Given some bar, and you want to make some cuts on it at some given points, right? Let's say you want to make, let's say the bar length is like ends up to like 10 to the 5, and you want to make like m equals 1,000 cuts. And so the cost of cutting is the size of the bar before you cut. The cost of cutting is the size of the bar before you cut it, and then you want to find the optimal way to cut it such that the cost is minimized. So like if I cut over here first, then the cost will be this entire thing. Then we split it into two. And this, if we cut it here again, the cost will be this, and then we split it into here. And if we split this over here, the cost is this entire thing, and then we split it here, and we just carry on. So like this problem, so how would we solve this? Naively, how would we solve this?
We can cut anywhere on the bar.
You have to cut where you're given cuts, and you want to perform exactly those cuts, but it's up to you to decide the order of those cuts.
Ooh.
And you want to minimize the total cost.
I'll probably use a range dynamic programming idea.
Yeah. So if we consider our range, like from dp, our entire like bar length, the answer will be stored in like dp from 1 to n, right? And so what would the total runtime be for this? O of n cubed. Well, n is up to 10 to the 5th, right?
Reasonable.
Yeah, so how can we speed this up?
Wait,
Go straight.
Yeah, what?
Wouldn't it be n squared m because you're like reinforcing over the cuts that you have in your range?
Yeah, so the neat part is you don't care about the entire length of the bar. You only care about the cuts specifically. So in fact, all you care about is the ranges of the cuts. And so we actually only need to store our dp from like dp from 1 to n, right? And the time complexity of this is
M cubed.
O m cubed.
Local strict, that's good. Same.
Actually, this would be local strickable because m is only 1,000. But if we like juice it up for like I don't know, 3,000 whatever. Yeah. So it's still too slow, right? So maybe we want to apply this optimization over here. So how can we prove this? So if you have like a bar with cuts at A, B, C, and D, how can we? This should be first for a min. Yeah. So how do we show that? So
Thank you.
cost from A to C, B to D will be less than the cost A to D, less or equal to. Right? So we can just do the math, right? So if we do the cost of cutting, or the cost for this range here, will be C minus A, right? So if we translate into its actual mathematical cost, we get C minus A plus D minus B less than or equal to D minus A plus C minus B. So does this condition hold?
Yes, both sides are equal.
Yeah, they're equal. So it turns out these costs are always equal. And this is pretty trivial to see that this is also holds. And so this pretty much gives us the green light to go ahead and try using Knuth optimization.
Oh wait, what about the second?
It's trivial.
Yeah, so the
Okay.
if we ever have, so if we translate these costs to D, so equal to D minus A, then we do some rearrangements over here, like think like C minus A goes equal to D minus B, and because of this is, or it's not
C plus A,
C plus A, I meant.
and then D plus B.
Yeah, because of this is like guaranteed to be bigger. It's guaranteed to hold. Yeah. That's let's see.
So I have a question.
Yeah.
So is like the runtime of like, I didn't really understand the proof with like the double summation thing
Yeah.
with optimizations. Is that at all similar to the proof we were doing with like the other one?
To be honest, I don't really, I couldn't really visualize like why.
Yeah.
Like the math just works out.
Okay.
All the like stuff cancels out pretty much, and you just look with that O n squared summation.
Mm-hmm.
Yeah. That's all I pretty much have for this lecture. Any questions?
Pretty good.
Nice.
I will say there is a third DP optimization called 1D optimization that's able to solve the recurrence of DP of I. You have to try to find minimize DP of J plus some cost I to J. That also uses this this idea of the quadrangle inequality and like monotonic transitions, but it's a lot more complicated. So maybe we can go over that next time. Also, yeah, this optimization can also